Give his head a little scratch. So last time we spoke about differentiation by first principles. This time we're going to use that to come up with these kind of rules, specifically one rule, the power rule. And to do that I need to introduce some new notation. So let's get started on this. Okay, so previously I've said if we've got a function, then the derivative of it is f prime of x. But there's another notation which I want to use. That is bright. So we had f of x and f prime of x. Now we're going to use y, and the derivative is dy by dx. It looks like a fraction with a d on the top, d on the bottom. It's not a fraction, right? What this is actually an operator. It's called an operator because it means we have done differentiation on y. Now, technically what we could do is write it like this, d by dx of y, but this is more common. So we take our y, whatever it was, say y equals x squared, and we do dy by dx of that. So you could do d by dx of x squared, and that would equal 2x. A nice way of thinking about this dy by dx is that it's like our old school gradient, right? Remember, m equals change in y and change over change in y over change of, I can't say it, change in y over change in x. That was the old school gradient. Now we've got y and we've got dy by dx. Let's tidy that up a little bit. As I said, it looks like a fraction, but it's not. We can't cancel out these d's. It is dy by dx. So this is two different types of notation. I believe the naming of it, it's like this one's Poincare and this one's Leibniz. This is definitely Leibniz notation anyway. It's a nice one. Oh, I dropped me thing. Right. So what are we going to do? At the end of the last video, we looked at a few things where it was like y equals x squared. We did differentiation by first principles on that, and we found that x squared became 2x. And then if we did it to x cubed, we found it was that. Now, if we kept going on and doing it over and over, you'd clearly see this pattern which I'm about to write. I'm just going to write it here, and then I'm just going to talk about it afterwards. Okay, this is it. This is the power rule. Power rule. If y equals x to the power of n, a little bit like our x to the power of 3, x cubed, then, right, that n could be any real number, by the way, then dy by dx, our gradient function, is n times x to the power of the original n, but minus 1. So a nice way of saying this is the power goes to the front, and then you subtract 1 off the power. This power went to the front, and then we subtracted 1 off the power. Now this is true for any value of n. So let's have a look at an example. Y equals x to the power of 4. Just going for the next one. So power goes to the front. Minus 1 off the power. Job's a good one. Let's do another one. Y equals 4x. Oh, let's not have the 4 yet. Let's just have x. Y equals x. Then that's like having a power of 1. So 1 times x to the power of 1 minus 1, which is 0. X to the power of 0 is 1, so it's just 1. Let's do one more. Y equals 3. Well, that's like y equals 3 times x to the power of 0. Or you could just say that's a straight line. It's just a horizontal straight line. It has no gradient. Yeah, that's fine. Okay. There was something I said in the last video where if you times your function by a constant, that doesn't actually, you could just take that constant out and then put it back in at the end. So here, I initially wrote 4x. So that would just be 4 times x. If we differentiate the x, we've got 1, so it's just going to be 4 there. If we change this one, we put, say, like a 7 there, then it's just going to be 7 times whatever that was, 28. So what we could do, now I like to do this actually because it makes it look a little bit nicer, is we go back to here and we say, well, let's put a constant in, an a, and that a is there, and that a can be any real number, and that works for anything, absolutely anything. Let's get a closer look. Right, let's make some room. Okay, now I said that this works for absolutely any value of a and n. So we're going to try a few different ones here. I'm going to do them here, and it's going to be amazing. Just going to point out that we can prove this using differentiation by first principles for any n. I spoke about like going through it and just trying different ones and spotting a rule. That would be proof by exhaustion, and you can't exhaust all real numbers. So we can do a little sneaky trick to show that it's true though, and I'll look at that at the end of the video. Right now, y equals x to the power of a half. Take the power to the front, minus 1 off the power. Half minus 1. Ooh, let's have another example. Remember in the last video that I said that if you have an equation and it's the sum of different functions, then you just differentiate each one individually. So let's have a quadratic. All right, so we differentiate each one individually, we go along. So 4x squared, differentiate that. Power to the front, 2 times 4, 8. 1 off the power. Okay, differentiate 3x. If we've just got an x on the end, it's just like chopping off that x. So comes a 3, and then the minus 1 at the end, well, that hasn't got a gradient, so it'll be like plus 0. So, oh, all right, we're done. That's it. Ooh, let's have a more spicy example. Let's have one which mixes together lots of different terms, but also this kind of business. Right, a bit more complicated. Clearly not a quadratic. Got half, minus 1, and then a 3/2. Okay, let's go through differentiating each bit. Half to the front, so it's a 2. Minus 1 off the half. There you go. Power to the front, so minus 1 at the front, so it's minus 1 times whatever we get. And it's x, so it's x. Minus 1 minus 1. Minus 2. That's interesting. We have to be careful that when you take 1 away, it goes more negative. And final one, power to the front, 3/2. So that's 3/2 times 2/3. That goes to 1. Minus 1 off of. There you go. Job's a good one. You know what? We could have added we could just add a constant on the end. 8. And it's still the same because that end bit, that one doesn't have a gradient, so it doesn't change anything. Ooh, I like them. Right, let's get rid of that. Talk about something a bit more spicy. Okay, I've got one last basic example. This is just one that I wanted to point out because we've got 4x to the power of 16 all over 5. Now, it's divided by 5, but we can actually look at this as being the same as that. So what we would write is, which we would simplify to 16 times 4. Oh, why have I chosen those numbers? 64/5 times by x to the power of 15. So it just works out perfectly fine, like normal. Something I've done on purpose here though. I see people do this all the time. They're like, oh, equation, differentiated, that equals that. What this is actually saying is that is equal to that. Well, you've not clearly said what this is. So something when you're doing differentiation, you have to be really clear with how you communicate your maths and say that dy by dx equals that. Then you're okay. Now what I want to look at, okay, we're going to use this side of the board, is we've differentiated things like y equals x to the power of half. Now some of you might have realized that that is actually just the square root of x. Looking at the rule, we can't differentiate square root of x because, it doesn't clearly translate to this. It has to be x to the power of n. That's just square root of x. But what you could do is you could simplify this into a form that you can differentiate. And that's a common thing that you're expected to do in differentiation. Use this rule for things where it's x to the power of n. So let's have a little example. Say it was y equals 1 over x, then obviously that's x to the power of minus 1 minus x to the power of minus 2. So we can use the power rule to differentiate things that don't look like it's x to the power of n, but we can simplify it into a version of that. Now I'm going to get 3 examples for us to go through, and then we're going to look at differentiation by first principles to prove that. Okay, these are our 3 examples, 1, 2, 3. First one's first, 8 over 3, 4th root of x. We're going to rewrite this. 4th root of x is x to the power of a quarter, but it's on the bottom, so it's minus a quarter. Okay, so 8 over 3 times what, x to the power of minus a quarter. Simple as that. Power to the front, minus 1 off the power. Minus 2/3 x to the power of minus 3 over 4. We could simplify this, not simplify it, I mean put it back into surd form, but I'd be happier leaving it like that. We don't like surds, and we don't like having x's underneath stuff as well. Okay, let's have a look at this next one. All right. Oh, we can't do it because there's a 2x on the bottom. And that's shared between the two. So what we're going to do, we're going to break up this fraction because it's 2x on the denominator. All right, 1 over 2x plus 4x squared over 2x, easy as that. Well, that's x on the bottom, so 4 divided by 2 is 2. All right, half x to the minus 1 plus 2x. So now we can go into doing the differentiation. Haha. Minus a half x to the power of minus 2 plus 2. This is great. We're just using the power rule over and over again with our laws of indices that we did donkeys ago. All right, this one looks a bit more spicy. Not only have we got an x on the bottom, but we've got 2 binomials multiplied together on the top. So what we want is to get it into the form of it's x to the power of something plus another x to the power of something. So let's multiply out those top bracket. All right, that was fairly easy. It was easy because there was a 1 there, so it's just 1 times 9. 1 times x at a 9x. Okay, so now we've got the x on the bottom. We don't like that x on the bottom, so we're going to do what we did here and share it between each of those terms on the top. I'm going to go straight ahead and just write it out, simplified. So I cancelled with one of the squares, cancelled with the x on the 10x. The 9 didn't have an x, so that's still over, it's 9 over x. But we don't want to write it as 9 over x, we want to use our knowledge of indices again. All right, 9x to the minus 1. Okay, so let's differentiate. What you might have noticed there is that I wrote a plus. Notice that the 10 disappeared, went to the next one, then realised that the minus 1 goes to the front, so it becomes a minus. So I quickly corrected that. If you're doing it in pen, you might want to go plus minus 9x to the minus 2. Still the same. That minus 2 looks huge, but it is in the power of x. Right, this was good. These were three very good examples. Now, what I'm going to do is going to do proof of this using differentiation by first principles. Okay, so this last little bit is a bit techie. That'll be good. Okay. This is going to be hard work, but we're going to do it. Let's quickly write down differentiation by first principles. That's differentiation by first principles. Now, I'm just going to say, I prefer writing dy by dx, but sometimes, like in this situation where we're putting a thing into the function like x plus h, it's better to write it in terms of f prime and f's, okay? So what we're interested in saying is, let's just look at x to the power of n. If our function is just x to the power of n, I'm not bothered about the a in front because we proved it already that you just take out the factor of a. So what this means is that our f of x plus h is x plus h all to the power of n. How are we going to expand that if we don't know what n is? So what we're going to do is do binomial expansion using just the thought that, well, we don't know what n is. So let's do that over here. So normal binomial expansion, let's start with an x. So it's x to the power of n plus, right, the next term is going to be, well, it depends what n is, but it's the first coefficient. Is it the first coefficient or is that technically the second? Anyway, it's going to be n, x to the power of n minus 1 h. Right, the next one is going to be, oh, what's the next coefficient going to be? Now this is where, I need my formula book. This is where we need to use the little equation for the coefficient. So it's going to be n factorial. It would be n choose, that was n choose 1. This would be n choose 2. So it's going to be n factorial over 2 factorial times by n minus 2 factorial. What that would simplify down to give us actually would be, so it'd be n times n minus 1. N times by n minus 1 over 2 factorial. That's what it would be. And there's an interesting reason for that, but that's more of like further maths, A-level kind of stuff. But all I'm going to do here is write that coefficient. That's it using the formula which is here in your formula book. But I've simplified it to that. And then we'd have like that, x to the power of n minus 2 and then h squared. The next one, right, this was how I could have written that. The next one is going to be like this. So this just goes on forever and ever and ever. So what we would do then, if this was up there and we're doing the limit of that minus f of x, well, let's do all of that minus f of x. F of x was x to the power of n. So what we'd get is let's write this nice. So we get all of that minus that. So that cancels with that. And all we're left with is terms with a h. Bam, 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 and it keeps going on forever and ever. If we then looked at, all right, so let's divide it by h. We'd cancel out that h. We'd cancel out one of those. This one would go to a 2, and every term that came after that would have h's in it. All right. Now we do the limit. If we do the limit of all of that as h tends towards 0, well, any term with a h is going to go off to 0. So all we'd be left with is this one, which didn't have a h because it cancelled with the h on the bottom. So it would be nx to the power of n minus 1 but there, that is it. Nice. Oh, I've just found my other calculator. I'm quite pleased that you actually get to use the binomial expansion for something good here, because that is a dry topic. Right.